It's a great pleasure to welcome you to the first real day, the second day, but the first real day of the Sloppy workshop. We're going to start off with Alexander presenting a mixed integer programming perspective on pseudo-Boolean solving. So without further ado, Alexander, please.
Okay, thanks. Sorry for the delay. I will talk about like a MIP perspective on pseudo-Boolean optimization. Jakob yesterday gave already good introduction on like a sub-perspective to mixed integer programming. Now I come from the other direction and give maybe a little bit of a perspective from mixed integer programming and then applied to pseudo-Boolean optimization. So maybe like a little bit introduction about me. So I originally come from the Zuse Institute in Berlin, which is well known for developing the skip solver, which can be seen as the best open source mixed integer programming solver. A lot of work has been done there on mixed integer programming. And even though I did not particularly work on the skip development, I worked more on practical problems there in healthcare, for example, in railway scheduling, steel production. I worked in the industry also for about 1 year. I did like smaller conference scheduling project and so on. So I deep dived a little bit into different industries from a practical perspective. So and now I kind of like, because I'm not here from Zip actually officially anymore, I'm still a guest at Zip, but I still have like connections to Zip, but I'm here by my own company that I founded like about 2 years ago. And in that company, actually we have the practical applications to optimize the hospital, if you want so. So the hospital is full of optimization problems and we want to solve them and want to improve the whole scheduling process within the hospital. And for this, we need a solver. So decided to develop actually sort of CP solver. So we want to have like an easy API to model like complex constraints within a nice, easy API language. But the thing is actually that the CP solver at its core runs the CP solver at its core runs a pseudo-Boolean solver, in particular a lazy pseudo-Boolean solver. I will get to this in the next slide, how this works particularly. The solver is written in C. So we want C because it's fast, and we want to do our own memory management, but also use other languages. But C is all the big solvers are written in C. And I'm familiar with C, so the decision fell to C. As I said, we want to optimize like in particular hard scheduling problems, and they arise also in the hospital sector. So I called the solver lazy CP. So the solver concept can be seen as follows. So we have like, let's say a real world problem. We have like an API to it. So the API goes to the CP solver. So we want to model all of our like real constraints in the real world within the CP solver. The CP solver actually then tries to encode the problem into a pseudo-Boolean way. So you can think of like more high-level constraints like cumulative or something like this that appear in scheduling. And very often CP constraints, they have a natural encoding. Like you can do, for example, in SAT, we want to use PB because of obvious reasons. We have more reasoning strength. And it translates basically the CP problem into a PB encoding. And then we trigger this search within the PB solver. That means we run on like a smaller formula. We run the PB search and we want to solve this problem. And then we have like dynamic callbacks. So the PB solver calls the CP solver again. Oh, is the encoding actually complete or is something missing? So it calls the CP solver and it tells like, oh, here actually is something missing in this high-level language. And then it adds a lazy PB constraint back to the solver. And then it has something more that it can work with and tightens the problem a little bit and then reruns this solving process. So until it at some point the CP solver does not add a lazy PB constraint anymore, then it knows like, okay, I'm done. So return the solution and I have solved my real world problem. So it's very, very similar to the lazy clause generation approach of the group of Peter Stuckey, which they in 2008 invented, but just for instead of clauses or subsolver, we use a PB solver. So because we want to have like stronger reasoning power. So and the whole thing requires lazy encodings of CP constraints. So every CP constraint needs to have some sort of like inner PB encoding, and every propagations that exist throughout the problem must be encoded by PB constraints. And yeah, the PB solver is also developed with the focus that we add a lot of lazy PB constraints during runtime. It means we don't have like one complete formula, but we want to add like actually a lot of new constraints. I mean, of course, conflict analysis does it also, but we want to trigger it from the outside. So we want to add a lot of PB constraints from the outside new to the solver during the solving process, yeah, by automatic callbacks. So this is the basic solver concept.
But will you also have, or are you also on the CP side doing like you have their standard propagator, say all different and all these things like, or
I mean all different. I mean I actually come
okay
to
the
example exactly. Yeah. For example, I mean all different constraint well known in the CP community. So in principle, so what is the all different constraint? We have integer variables in general, yeah, with or let's say with finite domains, and yeah, it looks like this. The constraint propagator or the constraint checker, it takes the domains and the variable itself, and so the constraint is true if the values of each pair of distinct variables is different. So all different. So, and of course, all different. I mean, it's not so hard to see. It has a natural PB encoding. You can encode it with binary variables that say xiv is equal to 1 if yi takes the value b and xiv is equal to 0 otherwise. Yeah? So it can naturally be encoded that, okay, every variable yi must take a value, so this is equal to 1, and every value can be taken at most once. So that's a very natural PB encoding, right? You could also do this in SAT, yeah, but I mean, probably you see already that SAT encoding would kind of like translate to something like a pigeonhole formula, and we know already that SAT solvers that are based on resolutions on pigeonhole formulas are a bad idea. And this is, for example, like a typical example why we probably want to have something like this in a CP world. And in operations research problems, like constraints like this, they appear all the time. Yeah, so you always have to assign something to something, and you always have like typical constraints that look like this. And it's a good idea to have a PB solver instead of a SAT solver for these type of problems. Yeah. Yeah, and of course it's exponentially strong, so we know that.
And now to make my question technically precise, so because also like what the CP people would do here, I guess they would fire up some version of Rejan's like all different propagation algorithms. Exactly. But this is not what you do. You just say, here's my PB encoding and let the PB solver work on it. Or do you also like, would you run Rejan on the
right now? I'm focusing. I mean, I have to admit the CP part is not super sophisticated yet because it's a lot of work. You need to implement all these propagators, and also I focus more on particular scheduling propagators. But of course, you could trigger a lot of other algorithms. You could take like flow approach or matching theory, or you could also just work on interval constraint, interval variables or something like this. Yeah, and then tighten the propagation. So I don't do this right now. But the idea basically is that we want to have some sort of like Boolean encoding of the CP problem, and we want to trigger everything lazily. So we want to have like a small formula that where we add just as much as we need in order to solve the problem. So this is kind of the solving concept. Yeah? So, but here, of course, I mean, it could also be natural to just encode it like this. So it's an easy way to just encode it like this. But right now, I don't do any particular more sophisticated CP techniques in the background that you could also use, of course.
I mean, it depends on how much work you need to, somehow partition the work with them to decide when to be there.
Yes.
Okay. So great. Thanks. Super interesting.
So okay. So maybe a few words to the solving engine in general. So where are we right now? Where am I right now with the features? So okay, I say the term CDCL. I think Jakob really, when he talks about CDCL, he really means like clause learning, yeah. But I mean with CDCL actually like constraint learning a little bit. So okay, it's probably a little bit confusing, but I mean compared to like full branch and bound or something like this, and I really mean constraint learning, that we learn constraints from the context, yeah. So you could replace the C like for clause also with C for constraints. So I don't know. So when I talk about CDCL, I mean like the concept of learning constraints dynamically during the solving process, yeah. So of course we run CDCL, yeah. So which is natural for the PV solver. So this is the method of choice. We add lazy PV constraints by user callbacks during the solving process, which is very important because we want to have this higher level language of CP. We want to like add dynamically new constraints to the problem. Yeah, as rounding sub, we have specific constraint handling for clauses, cardinality constraints, and PV constraints. I mean, there are like obvious advantages of distinguishing them for cache efficiency, for example. Yeah. So then we have specific handling of watch literals. I think some people here have also done good work on this. So of course, we didn't talk about it yesterday, but it's very important to make propagation very efficient. Yeah. So specific watch literal scheme. Then of course, Pseudo-Boolean conflict analysis. So we have a few versions that can be triggered or automated during the within the solver. So right now also mixed integer rounding is implemented. We have a lifted cover that I will explain later what this actually is, and we have the standard causal reasoning, which we actually want to avoid, but it's nice to compare, to just have it in order to compare the algorithms. Yeah. Then we have of course restarts. We also have heard a lot about it yesterday from like if we need to trigger restarts during the search process. We have constraint deletion strategies because we don't want to keep all of the constraints that we have learned over time because it slows down the solver. Yeah, we have a few pre-processing steps like some coefficient strengthening, redundant literal detection, but it's not too sophisticated yet. So there's a lot to be done. And I think in general in the Pseudo-Boolean community, pre-processing is still like a little bit of an open topic, and we can actually borrow, I think, tons of ideas from the MIP community again. But it's not implemented yet so much. Yeah, literal selection is very similar to VSITs, also rather standard approach. Yeah, you store a score for each variable. Yeah, what is maybe a little bit different that we don't have pace saving. So when I started to develop it, because actually I'm not a sub person, so when I started to develop this, it felt more naturally to me to actually store like separate values for, I mean, the negation of the literal and the literal itself. Because I mean, if you think about it in operations research, or if you have a variable, it actually makes a big difference whether you branch in the one direction or in the other direction. So because if it's like a crucial variable that you have and you branch in one direction and it triggers a lot on the other, and the other direction is rather uninteresting, you want to distinguish somehow whether it's interesting to branch on one variable or the other. So that's why I really have separate counters or scores for both sides.
So V-sits, but on the literals, so L-sits, as it were, instead of V-sits.
It's called L-sits? Okay, then, yeah.
I don't know.
I don't know. Yeah, so it's like, I mean, basically the list is twice as large, so I can iterate and check for the best. Yeah, I mean, I think it's a fairly standard way of like implementing some. So the features are rather standard, and now we want to actually get more into the like more sophisticated stuff. Slowly, yeah. So, and also borrow techniques from it. Of course, that's also one point why we do this workshop. And also in particular want to solve optimization problems, which is very important because I mean the whole Pseudo-Boolean thing is very focused on SAT still a little bit, yeah. But we really want to focus on cost functions and have good heuristics in order to get good solutions very fast. And of course, also do a little bit more performance improvements. Yeah, we want to have fast feasible solutions. We want to also have new lower bounding techniques and also from answer certificates, etc. So there's still a lot to be done. Okay, so yeah, we heard yesterday like an introduction to mixed integer program already, but it will probably intersect a little bit of what Jakob said yesterday already, but maybe another time, maybe a little different. So okay, what is mixed integer programming? Just to recap, so it consists of mostly these components. We have a cost vector. We want to optimize something. We have a linear cost function. So can be something in the reals. Yeah. Then we have a constraint matrix, which basically encodes our linear constraints. Yeah. So we have n constraints and variables. And in operations research, we call it always the right-hand side. Jakob calls it the degree. Yeah. So we call it right-hand side. So because it's on the right-hand side here, if you see this formulation. So, and then normally what we solve in mixed integer programming, we minimize the linear cost function. We have constraints. Yeah. Ax greater or equal to b. We can also write it smaller or equal. So it's also it varies always the definition a little bit. And then we of course we have variables that are either in the reals or intersecting also with the or like the cross product to integer variables, so it can be both. So, yeah, many problems in combinatorial optimization can be modeled in this way and solved that are very interesting, and we want to solve them. Very good. And yeah, operational research basically is highly built around the mixed integer programming concept. Yeah. So maybe a few words also to modern MIP solvers. This is far from like precise or exact or from complete overview, but just to give like a little overview still. So what modern MIP solvers consist of? So at its core, they run always an LP solver. So that means we want to solve like a linear, so-called linear relaxation of the problem. So that means we skip all the integrality constraints and then solve a continuous relaxation. They're normally solved by either simplex or interior point methods. Normally, within a MIP solver, you always use a branch and bound method, but with a dual simplex because you want to add new constraints, for example, a branching constraint or something like this. And you can warm start it with a dual simplex. So that means you have just a few iterations until you actually hit the next optimum in the continuous relaxation. So the method of choice in order to solve MIPS is always like branch and bound with a dual simplex. Interior point maybe to solve just the initial linear relaxation in the root node if it's very very complicated, for example, or very dense or very large the LP. Then we maybe solve it with an interior point method, but then make a so-called crossover and then switch to the dual simplex to continue to solve it. Yeah? So there's a lot of like LP theory also behind that, but I will not deep dive into that. Of course, there's a lot of additional techniques that modern MIP solvers encapsulate. So pre-solving, node selection. So that basically means, okay, they really build internally like a big search tree. They can switch from node to node in order to look further or explore the search space. So it's not like the stack-based view that we have in Pseudo-Boolean optimization. It's really they build a large tree, so to say. And they can switch from node to node in order to really decide, okay, I want to go to this node now to explore further the search space. So node selection, branching rules, of course, which variable do I take in a certain node to branch next to expand the search tree? Certain heuristics where I can, for example, just deep dive and try to find feasible solutions in order to get good solutions. And this is actually interesting. Conflict analysis is mostly, it's also implemented in modern MIP solvers, but it's only an add-on. Yeah, sometimes maybe you want it, sometimes maybe you don't want it. It's not, because in Pseudo-Boolean optimization, this is the method of choice how I actually solve it, right? Here it's just like an add-on. And it's also like we heard also from Jakob yesterday, it's more, they don't do it, at least from the original paper, they don't do it very intelligible. Yeah? So, or they don't do it very like intelligent because they still use these old methods of a sub-based approach. So they don't know really about Pseudo-Boolean reasoning. So of course there's also symmetry handling, etc., etc. So very sophisticated solvers by now. Of course, at its core is also cutting plane generation. So we have different classes of cutting planes, so that from which we could also borrow more and more for Pseudo-Boolean reasoning, I guess. So there's Gomori Quata, mixed integer rounding, cover, lifted cover, flow cover, disjunctive cuts. And very often when I solve the initial relaxation at the root of the node, then normally a lot of cuts are actually added in the root node so that I can initially improve the linear relaxation by a lot. Yeah? So in the general branch and bound procedures, like I solve the pure relaxation. If it's not infeasible or something, yeah, then I get like a fractional solution normally. So if the fractional solution is integer already, I can skip already, I'm done. So a lot of research actually focuses on, okay, getting that pure relaxation actually already admitting integer solutions. So that's why you want to have like cutting plane theory. Yeah? So where you always add like a lot of cutting planes so that actually your fractional is already integer. Prunes a lot of the search space and very efficient. Also, the reason why very often they're still like superior to Pseudo-Boolean solvers. But let's say it's fractional, then otherwise, if you find a fractional value, then you either branch on rounding up or rounding down and split the search space and solve recursively the corresponding subproblems that emerge out of this. Okay, also rather standard stuff. So heard about it yesterday. So yeah, but like a little note. So branch and bound, how it's done in MIP solvers is actually like DPLL, yeah, which is bad from our perspective, but actually with an LP solver at hand, which we don't have in Pseudo-Boolean. And it turns out actually that even if we do LP solving, or the fact that we have an LP solver at hand, it compensates a lot actually for having actually like a DPL, just a branching approach without any clause learning, because the LP, the fact that we can get integer very soon is a very, very strong property that many problems just, seem to benefit from. And yeah, we also have like, for example, like infeasibility proofs, something like this. So it's like we can detect infeasibility sometimes much, much earlier with an LP solver than with a Pseudo-Boolean solver. So really having LP at hand, and even though it's just DPLL in a certain sense, yeah, it compensates for a lot. Okay, I also want to explain a little bit about the geometry of a MIP. So how does it actually look like? Because we always look at it from a geometry perspective, not so much from a, okay, we just have variables or so, but actually, in fact, the MIP spans a solution space, a mathematical solution space. We can just really draw it here, for example, in 2 dimensions, where the MIP actually defines, if it's bounded, then it defines a polytope, but let's just assume everything is bounded and is not infinite in a certain direction or so. So then the cost function can be seen as this line that we want to push as much as possible in a certain direction. And it's also always, it's known that an optimal solution is always attained in a vertex of the polytope. So we will always be in such a corner. So for example, if we push this as much in this direction, we will land in this in this solution. As we can see, this solution is fractional, yeah? So it's not integer. So let's assume we will have an integer program here and we want to have integer variables. So then cutting plane theory on MIP, we want to always improve on, we want to cut away something from the solution so it becomes actually more integer. And if we can, for example, look at the so-called integer hull of the problem, that is basically the smallest inscribed polytope that contains actually the extremal integer vertices of this problem. So for example, we could add like this cutting plane, this cutting plane, this cutting plane, this cutting plane, and this here, and we would have like a complete integer description of the problem. And if we would know these cutting planes, then we could solve it actually just with an LP and be done. LP is also a polynomial time solver, so we can do it very fast. And also in practice, these problems scale actually pretty fast, but maybe more to that later. Okay, yeah, and we want in MIP, we want to have like strongest possible descriptions, so like integer hull. Yeah? And like the strongest possible sides here, they are called facets, and they are normally of dimension of the polytope -1. So there's a certain like level of how big the dimension of these like side facets are. We always want to have them like of large dimensions. So they inscribe or they define the strongest possible inequalities that we can get for a certain formulation. We are very interested in that, and this will also play a role then later on how we maybe do our conflict analysis and Pseudo-Boolean optimization. Yeah. Because if we have this polytope, then we can solve it by LP and we're done. So and of course, when you run a MIP solver, then you always have like something like an integrality gap. So you can also prove that you're 5% from the optimum if you just compare, like let's say, the best integer solution that you have found with the one that the LP relaxation gives you. So we always have also optimality guarantee, and we try to also do something like this in Pseudo-Boolean reasoning by generating like answered proofs in a certain direction, in an infeasibility direction. So maybe a few, because we also addressed the topic of proof systems also a little bit. So now the topic of proof systems maybe from a little bit of a MIP perspective. So we can, as I said, we can define this polytope P, which is the polytope of the linear relaxation if we skip all the integrality constraints. And then we can also look at the integer polytope that is basically the same one, just intersected, or maybe I should actually say the convex hull here, so it's not mathematically very precise here, but actually we look at the convex hull of P with the intersection of the integer points. So this is the integer polytope. So, and we are interested, on how to get this. So because also if we don't have an integer point and we want to have, for example, an answered proof, then we want to have like a strong proof system that can quickly show us, okay, there exists no integer solution. So, and what we can consider here for each constraint J, we can define like non-negative multipliers, and we can just add up with according to these multipliers, all the constraints and all the right-hand sides, and we can round these sides up. So then we get a new inequality, basically. Yeah? So, and we can, let's say, we take all the possible multipliers that we have and then take the intersection. So, yeah, so basically we can vary around, and then we take, because of these rounding steps, we always push it a little bit in. Yeah, so we make the inequality always a little bit tighter. Then we can define the so-called quarter closure. And yeah, that's basically defined if we do it for just for P0, which is supposed to be like the original polytope. We get like the first quarter closure. And it can be shown that this is again a polytope, yeah, and that it's of course a little bit tighter than the original polytope. So, and we can actually repeat this procedure. Then we take like P1 and do this again with the new inequalities because it was a little bit tighter. Then we can do the same procedure again, make it a little bit tighter, make this procedure again, make it a little bit tighter, and so on. And actually, a big theorem is that, yeah, very famous theorem is that there exists a finite number of how much we have to do, of how often we have to do this until we actually really get the integer half. That means it's a proof that, for example, for example, if we're looking for infeasibility proofs, we can do this like a lot. Then in the end, we will find eventually an infeasibility proof in finite amount of times of doing this procedure. But the problem is that we do not really know like how to describe these things. But in principle, we can use this procedure in order to generate a proof. Yeah? And this K is also called very often the quarter rank. So it's very similar, actually, I think, to proof complexity also in other areas. But this is the MIP version, so to say. Yeah? So there are definitely intersections. So, and yeah, maybe let's switch to more in particular, because we are not generally interested so much into integer problems, but actually in 0-1 integer linear programs. So let's go to this one. So the definition is pretty much the same. So we have a binary program, so where we just assume that all the variables are now like between 0, either take value 0 or 1. So now this defines a polytope that is now a subset of the hypercube. It's not too hard to see, right? And yeah, it's equivalent to Pseudo-Boolean optimization. So rich history of quantum theory, and maybe like a theorem that's actually also know the quarter rank of 0-1 polytopes is actually polynomial. Yeah. Also, there exists also a lower bound that is actually in n square, I think. That was a kind of recent result from 2013. So what does it mean actually? It tells you something about like, I mean, because if you go from proof complexity point of view in SAT, for example, you're always interested like, okay, how many steps do I have to do something? It's like this tree-like proofs and so on. And this, I think, gives you like an idea in the MIP world on like, what is the depth actually on an infeasibility proof? How big, how many steps do I have to really make in order to actually reach some infeasibility proof? But actually the theorem here states that this is actually polynomial bounded in the number of variables, which is for 0-1 integer linear programs actually a good news, because it kind of says that it cannot become like arbitrarily large or exponential or something like this. So we just need to, basically means we just need to find out how to set the coefficients right, and then maybe we can eventually get an infeasibility proof on unsuccessful replicate. Yeah, quite easy. Oh, not easy, it's hard. But yeah, but it says it's bounded at least polynomial. That's good. Okay, now let's consider in particular the knapsack polytope. So a knapsack polytope is actually given, or the linearization is given, or knapsack inequality is given by this form. It's just one cut. Yeah, I mean you have the hypercube, and then you have like one cut in between somewhere. But does not mean that the integer, so the integer hull can look very different. It can have like many facets. Yeah, so it's not clear, even though you have just one cut, it induces, if you want to have an exact description, it can like look very complicated actually. And it's not really known in general how to get like easy all the facets of a knapsack polytope. But there's a lot of studies have been done on how to actually generate strongest possible inequalities for I mean, let's say a subset of strongest possible inequalities of a certain knapsack inequality. And in particular, there are limited cover inequalities. There's like these are certain classes of inequalities that you can get from there that can, under certain circumstances, also define facets of the associated polytopes. Yeah? So, and this is in particular interesting because what we do in pseudo-Boolean optimization is consider exactly those inequalities. Just, I mean, greater equal to, but it's equivalent. You can transform them back and forth quite easily. Yeah? So it's very interesting to study these sorts of polytopes and the induced integer hull, and which inequalities are strongest possible in a certain sense that we can, for example, use in conflict analysis. Yeah? So, because from a MIP world or from a MIP perspective, you always thought LP relaxation, we always want to have like the strongest possible description. Yeah? And I think, I mean, it's still a little bit of an open research field, but there seems to be a connection between the strength of to me at least, there seems to be a relationship between the strength of an LP relaxation and how good we can do pseudo-Boolean optimization on that formulation. Yeah. So, and in the MIP world, we always want to have mostly strongest possible inequalities in order to cut away as much as possible from our linear relaxation. If this is the same in pseudo-Boolean optimization, it's not really clear because it's more, we have these logical things and we have all these heuristics on top. So it's not really clear. We also want that, but I think there's indications that we really want to also have like strongest possible formulations for our problems. Okay, so for example, how does a knapsack cover look? So knapsack cover, we also had it yesterday already. So knapsack cover, so a knapsack cover is a subset from my original formulation. Or actually, okay, I think I forgot to mention actually what knapsack cover is. I think I had it in one slide, but maybe I missed it. So, I mean, we can define knapsack cover inequalities. We had it yesterday already. So if we have like a minimal subset that we cannot all at the same time be one, we can actually enforce a constraint like this so that at least one of them must be actually put down to 0. Yeah. So, and the cover is minimal if the inequality is actually satisfied if we just like erase one out of them. Yeah. And and we are always interested in minimal cover inequalities normally because otherwise they're dominated. Also in a geometric sense. So for example, we can look at this example. So this is the linear relaxation, and it's not hard to see what the integer hull is. So we can basically draw this constraint, and this looks like x1 plus x2 is equal to 1. So this is like I mean, that particular is also a facet, yeah. The particular example, so we want to always have like these strong inequalities that cut away a lot from this useless parts that we're not interested in. So, so now we extend this a little bit to lifted knapsack covers. So we can always use, I mean, the idea is that we can start from this point, yeah, that we have a subset where we can enforce this cover inequalities. But this is not the end of the road. We can actually improve this constraint by adding other elements that are not in the cover to the constraint and defining certain coefficients for this. And the question is like, how do we compute such coefficients in order to improve this inequality and make this stronger? So, assume we're given knapsack inequality and an associated minimal cover inequality. One is, of course, this is wrong. Yeah, so this must be here C minus 1. Yeah, sorry for this. So this is not a minimal cover, so here must be like this here must be written here. Yeah, C minus 1. So this is wrong. So and assume we have a minimal cover inequality. So basically this here just without this alpha term. Yeah? And so now we consider an element J that is not in the cover yet, and we want to actually integrate it and just find a coefficient for this so that this inequality is still valid, yeah, in order to make this stronger here, this inequality. Yeah? So the more elements we put into this, the stronger the inequality becomes. Yeah? So now the question is like, okay, it should look like something like this. Yeah. Now the basic question is, how big can this alpha be like at maximum? Because also we want to have it with maximum coefficient the tighter the inequality gets. Yeah? Clear. So now, I mean, we can just assume that xj should be 1, and then we just compute this term here, right? So we just like put this to the other side, and then alpha j should be 1. Yeah, so the 1 cancels out. This is smaller equal to this term, and for this here, we just have to find like, okay, how large can this term here be at most? such that the original inequality is still satisfied. So we basically just compute this here, and this is nothing else than a simple knapsack problem. Yeah. So we're interested in computing this term, and this term corresponds to a knapsack problem. If we have integer data, which is normally the case in pseudo-Boolean optimization, yeah, we can also solve it by dynamic programming pretty fast. Yeah. So then it becomes this term, and we can solve this in O B times C with integer data. So relatively easy. Then we can actually set, okay, we have an upper bound on this upper j, and then we set it to this upper bound, and then we have a new coefficient in our knapsack cover. So it's a very common procedure in mixed integer programming. So yeah. So and now, of course, we can repeat this procedure. I mean, once we lifted one variable in, we can do this for the other variables as well. So we can actually consider a sequence of elements that are not in the cover, yeah, of all the elements that are not in the cover. Consider any sequence and yeah, define it like in a recursive way, then like this, like so the next element is equal to this. Because just we changed the objective function here in this term a little bit, yeah, but still such that the original inequality is still satisfied under the condition that we fix this variable to 1. So it's again a knapsack problem that we solve here. In particular, actually, it's a knapsack problem. I mean, we get this inequality in the end out of this, and we can actually reuse the computations also, like recursively. Yeah, so that means in principle we would have now, okay, in every step we need to solve this knapsack problem again, but actually we can reuse a lot of these computations because I mean, if you solve a knapsack problem in a dynamic fashion, you just fill out a table, yeah, but you have one part of the table you have dynamically filled out already, and then you just add a new row, and then you can make computations based on these values that you've computed already. So if you have a fixed sequence, you can actually reduce this complexity from bn squared to bn. So yeah, so something that's still to mention, so different lifting sequences yield also different inequalities. Yeah, so the idea is basically I have a certain sequence and I push this as much as possible to the side until I hit like a facet, and then I go to the next one and push it as much as I can until I hit the facet and so on. So it's like a extreme method somehow. Okay, push it to the maximum, push it to the maximum, push it to the maximum, push it to the maximum. But this does not yield, I mean, not every facet that a knapsack polytope has can be obtained this way. So there can also be something like in the middle between that are not lifted cover inequalities, for example. Yeah? So the type of facets that a knapsack polytope has are much more variety. Yeah? So, but it's still a very easy and efficient method of how you can compute them. Yeah? And we also want to make use of something like this in our Pseudo-Boolean solver. Yeah, and we can solve it like, it's still quite expensive, but maybe we want to do it sometimes in our solver. Yeah? Okay, so.
Can you say something about just we're trying to parse the math here? You mentioned that clearly the choices of the initial cover and the J ones up to J case will be important, but should I think on this in order for this to sort of make sense? Will we start with an initial cover of variables with fairly small coefficients, and then we try to lift variables with heavier coefficients?
The cover that we have initially is actually given by either the propagation or the conflict. So there's actually no choice in that.
Okay.
The choice is just given by the lifting sequence in the end. So where we
can. But for instance, if I suppose that I got a cover over all the heaviest variables, then sort of the lifting sequence just I wouldn't be able to lift, would I?
Maybe. I mean, it can also be that these coefficients can be 0, of course. Yeah. So if this is like equal to C1, and normally if you have very small coefficients, it can happen. Yeah, they just don't play any role in your description. But I think it's. Yeah, the question is, I mean, in a logical sense, in a pseudo-Boolean sense, do you want to integrate them? I don't know. In a geometric sense, probably they're not that important, yeah, because they just have very small coefficient and they don't contribute to anything. So they probably, I mean, geometrically they don't hit anything important. So this is my interpretation. So yeah, but of course, I mean, on the other hand,
somehow, I mean, the reason you're able to lift is like, for instance, if xj1 or l+1, or if suppose it has a big coefficient, but it's part of that, like, what is, I'm trying to understand what's happening. So Like if it has a big coefficient and you say that is 1, then you can say, well, if that is already contributing to my knapsack, then the sum of the other guys has to be much smaller than before. And then alpha j is going to be something nice. And then you're going to be able to lift with a big coefficient. That is sort of what we were hoping for to happen. Is that right?
What you can think of maybe a little bit, I mean, of course, it depends on the sequence. Let's say you have your fixed cover, and then you have like elements that are not in the cover, and now you can determine a sequence. Let's say which sequence do you want to pick. So of course, you could start now with the ones that have heavy coefficients, and they are very likely to be lifted in because they have large coefficients. And if you solve this problem, then yeah, it's most likely that they have something that is non-zero. Yeah. So you could also start with the small ones, maybe, or like medium ones, and then okay, maybe it works. They still have something, and then you can start also later with, for example, heavier ones. And they might also still be integrated, but they have a lower coefficient. So there's kind of like the first ones that you try to integrate, they normally have something because it's more likely. But the problem here becomes, yeah, I mean, you have more variety then in order to fill out this knapsack, and so they are more likely in the end to become zero. So the first ones are the ones that you want to focus on. Okay, I want those to be integrated, and they should have some coefficient. And if it's very small, it's maybe not likely, maybe they have a zero already, but if you have to start with medium or bigger ones in the beginning, they will have non-zero coefficients, but the strength of the coefficients will degrade throughout the lifting process. So approximately like that. Yeah? Okay. So, all right. I mean, of course, you can do some relaxations to this whole procedure. I mean, this is right. I mean, you can also show that these lifted inequalities are actually defined facets for the polytope they are describing. So they are as strong as possible in that sense. But like the full sequential lifting, if you think about it as a subroutine in compact analysis with B times N, I mean, it depends. Maybe, I mean, you can make it very cash efficient also. Also, Skip uses like subroutines like that, I think, internally. I mean, can still be too slow. So you can do also some relaxation or approximations to that. So the simple one that's also implemented is like, I think it dates back to Balash, so like a very early paper where you just like sort the coefficients once and then you make an index comparison. Then you can just basically pick like, okay, you sort them by the heavier coefficients ones, and then you look, okay, I have a new variable that I want to lift in, and you make a coefficient comparison with the partial sums of the first elements. And if it exceeds this one, and it has a large index, and if it doesn't exceed the ones, then it has like a smaller value. It's maybe too complicated to, but actually it's just based on you sort them once by the coefficients, then you just make a simple index comparison of the partial sums in that list, and then you can determine like the lifting coefficients based on that index where you find this, where you make this comparison of the partial sums. Yeah, so has a reduced complexity of C log C. You can even do something that is just in linear time. You can just look at the biggest coefficients, and if you have like a variable that has a coefficient already bigger than the coefficient in the cover with the biggest coefficient, then you can immediately set it to 1 already, yeah, because or 2 even, yeah. So there's also like linear time approximation to this, and sometimes it can be useful to, I don't know, switch back and forth. Yeah. Okay, so I still have an example, but I think I'm talking too much. So I think the idea is actually rather clear. So maybe just very quickly. So we have just an example. We have a knapsack inequality. Yeah, from that one we can just define a cover, for example. Yeah, so these inequalities here define a typical cover inequality. I mean, it's to be noted that cover inequalities are clauses. Yeah, so using cover inequalities standalone will probably not benefit that much. So that's why it's just a little bit of a reversed approach. We reduce the constraint first to like a clause, and then lift in additional coefficients laterwards. It's like a little bit like an antidote to weakening. Yeah? So if you think about it, so it's a little bit like a reversed approach. But I mean, we have proof that they are sufficiently good so that they define maximum possible inequalities. So maybe I think it's a good approach. Yeah, then you can consider a lifting sequence, and you can compute your things, and then you get like certain coefficients for those. And then you see that you made from this cover inequalities, you were lifting additional variables in, and you get a much stronger inequality. Yeah. And here, for example, you can see like for example, this one here, alpha 1. So because this has a very rather large coefficient that was lifted in later will also have a rather large coefficient here. So yeah, but I mean, you can also change the lifting sequence and maybe get a different inequality.
And which, again, the lifting sequence is just going to be, there are some heuristics for this, or like your gut feeling tells you.
This is something that I'm trying to experiment right now. So I'm not sure. I mean, right now, I mean, or like the naive approach, how I did it in the first way, I just took the order of the pure order, because you don't need to do anything. It's just fast. You just go linear through it, and you don't need to do any extra computations. But yeah, my gut feeling probably would say you should probably do something to lift in variables with high activity, based on the score or something like this, or some variables that fit to the conflict constraint, so that you maybe can cancel out something or strengthen something, or something that maybe where saturation maybe can benefit from, or something like this. So I mean, there's different approaches, but I don't know. It's also to be noted that, I mean, it depends also on your problem whether, I mean, you actually are able to lift in a lot of stuff. So some problems are just, they don't have that many coefficients where you can lift in a lot. But yeah, but this is an open research question on which variables to lift. But you should, I think, make a choice on something that seems more to your problem. Yeah. Okay.
Question: does it make sense to try to create more program inequality by just swapping variables? For example, here you can see that x4 and x5 are both weights of R4. So in the end, can you just say, okay, I take the same program inequality, but I replace x4 by x5?
Sure, it's also a valid cover inequality. It's, okay. By definition, it's exactly the same. But, yeah.
And is it?
But the thing is, the cover inequality, the initial one that you have, I mean, this is just an example, but in your pseudo-Boolean reasoning, it's normally defined already by either your conflict, or, I mean, there may have some variety, but normally when you propagate something, you can always extract a propagating clause from that, which is basically the cover inequality, and then actually this is kind of fixed already. So because you always unit propagate, and then so you don't have a choice actually to replace something. But in principle, in order to, I mean, within your pseudo-Boolean solver, you don't have the choice probably, but in general, of course, you can switch it here. So it would be equivalent in that example.
Okay.
Okay. So then there's mixed integer rounding. We'll also not go too much into details of this. I mean, this is work from also Jakob, Julian Maxey, also from SUSE Institute. They wrote a paper and tried to implement this like in the skip solver. And also, I'm not sure if it's in rounding stuff already. I mean, there's a little bit different definition that Jakob used yesterday. So this is more like the MIP definition of a mixed integer rounding quality. It's also, so it's so where these f's here, they are like the fractional part of something, then you can divide something. But I mean, these inequalities are also rather strong, normally in a setting. But I think the difference is between these lifted cover inequalities and these inequalities is that they are probably more general. So it's more likely that a wide range of variables are included somehow in the inequality, while this lifted knapsack covers, they really go like heavily for for a smaller set of variables, but have those with high coefficient, while this is a more broader, more general inequality that tries to get like a broader range with higher coefficients. But in the end, I think they also don't necessarily define facets. Yeah, so because this is exactly, I mean, kind of the approach of Morikawa, you need to have like multiple rounds in order to maybe get the facet. So it's not guaranteed, I think, that they define facets necessarily. So there's probably research under which circumstances they define facets, but in general, I think they don't. Okay, I need to really hurry up. Okay, this is just another example for mixed integer rounding inequalities, and yeah, actually, just as a comparison, you have different division variables, and so it always depends on a division coefficient, and you can generate multiple mixed integer rounding inequalities. Even though in the solver itself, I mean, I think you always need to choose a specific one if you want to make it use in a Pseudo-Boolean solver. But then you can make a comparison, for example, to between mixed integer rounding inequalities and the lifted cover inequality. And here you see, for example, if you do the lifted cover inequality, you would get something like this. And okay, this here should be not the negated ones, I guess. So okay, just forget the bar here. So then you can compare those here a little bit, and you see actually that, I mean, if you could look at the ones with coefficient of 3 here, I mean, this is stronger here than the maximum, like the best one was coefficient 3 on the right-hand side. So this here has 1.5, but this here has 1, if you consider this for 7. So under certain circumstances, I think the lifted covariate growth can be stronger. I think I'm not sure if the reverse is actually true because I mean they normally always define facets, so for the associated subpolytope. So I'm not sure if the reverse can actually be true. Need to think about it a little more detail, but I think it's not too hard to come up with a proof or idea. So my guess is not. Okay. But on the other hand, I mean, they can still be useful because you can integrate a broader range of variables at some point. Even though they're not facet, they can be useful in a Pseudo-Boolean setting. Okay, so yeah, I will not go into detail. I talked a little bit already quite a lot about like the difference between PD solvers and MIP solvers. So I'll just skip this. Yeah, Pseudo-Boolean conflict analysis now. I mean, I also talked a little bit about this already. So yeah, wanted to point out a little bit the difference between like what rounding set do and what we actually do. So, but the main difference is actually, I mean, this goes a little bit away from this point of view of the weakening approach. You normally consider a reason constraint and then you try to reduce the coefficients step by step and step by step. So this is what the rounding set also does, and then they do some division in between, some saturation in order to improve it. But what we do, and you always need to guarantee that the reason constraint is propagating tightly, so we don't get any, so we don't lose any information about the conflict. But what we basically do is, I mean, I said it already. Okay, this is just an example. So what we do is actually we do pretty much the same. We just look at the reason constraint, but we expect a cover, and then we lift the cover, and then we have also a tightly propagating explanation for the propagation. And then we just add it to the reason constraint, also with a little bit of weakening in between, so that yeah, you just get, yeah, you also just get in the end like a conflict constraint that looks a little bit different, can look a little different, but can be under circumstances maybe a little bit tighter because you get a tighter constraint in the end, but can also just look different. So it's not really clear to me. It's an open research question when to use what. So I think they're complementary approaches. It's not like the one is always better than the other one. There are different philosophies are behind that. So we just really want to find out, okay, when do I use this one and when do I use this one? Okay. Yeah, just said it. Okay. Yeah, I mean, also said like,
is it clear like how if you use this lifter, obviously if you would use just a naive cover, that would be a clause, so it would be tightly propagating, so conflict analysis would be guaranteed to work. But does the same argument also go through for the lifted? Like how do we know that conflict analysis will work? It
just works because actually the falsity of the constraint will not change. Actually, it will always be, so in my example, for example, it will always be actually exactly -1. So
okay.
So
because a few minutes offline, I would figure this out.
Because I think so. Because I think you always start with a cover, which always has falsity 1. I mean, under the circumstance that your conflict constraint is already a cover. I mean, there's also something that you could do. You can start with a conflict constraint already and also lift the cover. So, but yeah, you could find it out. So it's always guaranteed for sure. Yeah. So because it's, I mean, by default, the clause is already tightly propagating. So there cannot be, you just lift in other variables that have nothing to do with the propagation in general. So you start already with something that is propagating, and this with a clause or with a cover constraint. Yeah, so that's why I mean, it's maybe a little bit offensive, but this weakening seems a little bit odd to me. So because I always like trying to figure out which by which I can reduce a little bit, because I mean, the whole operations research literature is full of strongest possible inequalities for a knapsack polytope. So it seems rather natural to just take the strongest possible that we know and we know how these facets kind of, or a few classes of these facets look like, just use them, because they're strongest possible. And what we actually want to do, we always want to use the strongest possible. This automatically transfers to Pseudo-Boolean reasoning. It's not really clear because, I mean, they have logic inside. And so it's not really like this geometric view that you can cut something away and that's automatically better. You always have like certain dependencies and heuristics on top. So, but the general approach is always you want to have something like as strong as possible. So and that's why I think like using facets is at least not a bad idea. Yeah.
Just to say, I agree that lifting is definitely very weird. Sorry, weakening. But
Yes.
but also that in the lifted curves we also like lose. There are variables that we fail to lift, right? And those are in some sense
Yes.
weakened away, but we don't use that word. So
Yes,
it would be interesting to understand. Like it's
that's
definitely odd, but how are they related? I don't fully understand.
I mean, it's also, I mean, I just mentioned a few other, I mean, these are for mixing the rounding and lifted cover are the most common ones, but there's other facets or other approaches on how we can separate or introduce new facets for this. So it's definitely not the end of the road, and we have to investigate probably all of them. So and when to use which ones. So okay. Yeah, and also, yeah, strong IP relaxation led to, so this is my personal opinion, so strong IP relaxation led to better PB reasoning. So it's my little bit personal take. We can see it actually very well on the pigeonhole formula, if you use it in sub formula. So because if you run a LP solver on a natural CNF pigeonhole formula, it's extremely bad. Yeah. So this is for me like actually the example where this shows up already. So if you have a bad IP relaxation, then or bad encoding, then also PB reasoning is bad on that. Yeah, and we want to, so this is one of my, what I actually would like to discuss or figure out. So what's the relationship between the strength of the IP relaxation and the quality of PB reasoning? Okay, I did some also experiments with my solver, but I'm not sure. I did some experiments on MIP on particular scheduling instances that I did. So just maybe short take here is that on certain instances from the MIP that are quite big, it found solutions pretty fast, but my optimization approach was not very smart, and I'm trying to improve this now, so it's not competitive yet with any MIP solvers yet. But it was interesting that even for very large problems where LP solvers actually have a problem, yeah, because they have I mean, I assume that even the LP has problems in solving the root relaxation because the problems are so big. I mean, the PB actually found initial feasible solutions like pretty fast, which I found interesting. Yeah. It was 17 million constraints and 8 million variables. It was found the solution super fast here. While I think if you want to run a MIP solver, it already like, I don't know, it's probably stuck in solving the relaxation. I didn't try it out, but my guess. Okay, so to complete, so my research interests, because I should do a pitch. so I consider MIP more like a first order method because we have like gradient or dual information. Right? I consider Pseudo-Boolean optimization more as a zero order method because we have no real gradient information. So it would be interesting to how to simulate like dual information in a Pseudo-Boolean solver. So then next question would be interesting is how to make use of more than two variables at a time in propagation or conflict analysis. So we want to integrate more, something like this here. Yeah. Any other strong derivation rules than the standard ones like saturation, adding, and so on? I mean, Jakob mentioned yesterday already a few, but I think also proof complexity wise, it's still a little bit open. Yeah, effect of better P relaxation on PBO. I mean, operations research concepts like column generation in PBO would be very interesting because it relates to extended resolution or like higher order proof systems. Yeah, would be very interesting. But column generation actually makes use of dual information, so maybe it's somewhat combinable. And yeah, also technical details on core guided search because this is what I'm implementing right now, and I want to know about someone who has implemented it already. So about certain technical aspects. So yeah, so thank you. Sorry, I probably.
Thank you. So any questions for Alexander from the physical audience here, from the virtual audience? Yes?
It makes sense when you have your cover lifted version to do some kind of post-processing where you remove one variable from your cover and you try again to lift it to see, okay, maybe I can change these variables and add new variables to lift it. So you will get a new cover and you can just repeat your procedure again. And so you will produce more than one differential.
That's definitely thinkable. And actually, it's a good idea because I think the problem always what we do in conflict analysis, we don't know what happens down the road, right? And we always want to have something that somehow, I don't know, converge to some nice formula in the end that we can use somehow, or we can like apply additional saturation where it cancels out more stuff. And this is, for example, something we don't know yet if we just pick one, right? And if we can a sort of like backtracking scheme within conflict analysis, I could think of something like this. But the question is always like with performance, if this actually it really pays off in the end. But yeah, it's not clear like which constraints to use. It's a very broad, open question, I guess, in Pseudo-Boolean. But you could think of something like this, yes, of approaches to do.
Yeah, may I ask a question? We also have a question from the virtual audience.
Is your solver open source? Can I try it?
No, I have a company. It will stay commercial for sure. So this is clear already. But I mean, I would be interested actually, of course, to compare it. I mean, I also want to write papers, or I still have to write papers because I have to finish my thesis, and I still definitely will write a paper about this to do some comparisons. So, but in the end, it will definitely not be open source. So, unfortunately, I'm sorry. Yeah.
So I think Ambros Glaxner had a question.
Hello. Hey, Alex. So I did not fully understand how the conflict constraint comes into your reasoning. Can you
Yes.
maybe go back to the slide where you
Yeah, I didn't mention
explained
it
that?
in detail because
No.
I know this is too far already.
Here, yeah.
Here probably. I know in my approach. So this is
Yes.
here probably.
Yes, exactly. Where does the conflict appear here?
Yes, I mean, I didn't mention it explicitly because I considered a little bit about like separate approaches. I mean, you can change the conflict constraints. You can just take the conflict constraints that you have and then just add the lifted cover inequality, for example. Yeah.
So I guess I'm confused. Just a question was like bullet 3. Do you mean adding C lifted and C conflict probably, rather than C lifted and C reason?
By adding C lifted,
because
C reason, C conflict shouldn't be. C lifted is
Okay, that explains, that answers my question.
Also,
I mean, the lifted is just a converted reason constraint. Yeah, so that should not. So
I think there's the same confusion on the previous slide also, that there's a conflict missing.
I'm sorry, maybe I did a mistake. So, but this is definitely wrong. Yeah. So in point 3 should not be C reason, it should be C conflict. So because of course, the lifted one is just a transformed reason constraint, and you add it to the conflict constraint in order to cancel out xi. So, I mean, this is how it integrates. But maybe a broader question is like what you do with a conflict constraint. I mean, there's different approaches. I mean, you can first of all keep it, because the conflict constraints, forcibly nothing will change, and you will just cancel out something. But you can also, of course, what you can do is you can also perform on the conflict constraint. You can perform also a lifted cover inequality. So you can narrow down the conflict to something that's maybe more useful for you. But you don't have to do it, so it's your choice. So I consider this a little bit like as complementary approaches, what you do with the reason constraint and what you do with the conflict constraint. You can just use the conflict constraint as is, and then add the lifted cover inequality on top, so to say. But you can also narrow down and improve the conflict constraint a priori already. Yeah. So does that go into the direction?
Yes, perfect. That lifts the confusion. Thanks.
Yeah, sorry. Yeah, this was here. There's a mistake on the slide. I'm sorry. Yeah.
And just to ask about this slide also, was this should we understand like you say that there's this lifted reason constraint, and you say you can also apply MIR to it? Is it or? Yes,
exactly. I mean, just as a comparison, I also applied. I mean, the thing is also with MIR, I think, as far as I understood, in order to make it work in pseudo-Boolean reason, you have to select a specific division coefficient. Yeah, I think it needs to be the one of the variable that cancels out. So
yes.
So I think you don't have the choice actually, and this is just to compare on how this would compare if you, use division of 3. According to the approach that you have done. Yeah. So how this compares to the lifted cover inequality, and you see. What I just wanted to show is actually they look quite different. So it's not really clear which one is better. You could also, in order to get the right-hand side same, you could just multiply the C lifted by 2. Yeah. But then you get something incomparable somehow. Yeah. So yeah, it's open. It's not clear like how to use it, but in general, I have the feeling like MIR inequalities, they are broader. So you integrate more variables, maybe with decently quality coefficients. And while the lifted ones, they are just more extreme and going into a particular direction that you enforce them to. But MIR are more broader. The question is, for which problems?
But like you're saying, lifted couple constraints seem more compact or something?
Yeah, they're smaller, I guess, yes. So in general, you don't integrate that. I mean, it always depends on your problem and which type of inequalities show up actually in your problem. So probably your real world problems have much more structure so that maybe they will even collapse to the same. Yeah. So, but I don't know. It's
interesting. I mean, I don't think we understand this, or at least I certainly don't understand this. But I think if you look at the heuristics that appear in running set, a lot of them, like a lot of this mysterious weakening is about somehow getting constraints that are maybe not semantically as strong, but they're more compact. And since conflict analysis is such a syntactic operation, sort of maybe you're willing to take a weaker constraint, but it has fewer variables, so there will be less, less of a mess in future conflict analysis steps. This is not anything that we understand rigorously at all. It's just
I mean, even though compact in a sense, for example, if you have a click inequality, so where you have like smaller equal to 1 or so, and then you have a cardinality constraint, I mean, like all coefficients 1, I mean, they will collapse to the same. So, I mean, it's not that they only integrate like a small part. I mean, they can also integrate like the full range if it's strong enough. So, especially for very, at most 1 constraints or so. This is, I mean, it will still be the same. But in general, broadly speaking, I think they're more compact, yes.
Okay, so I think let's thank Alexander again.
Thank you.